So now let's solve a few interesting questions, right? So it says the chip select logic for a certain DRAM, right? For a certain RAM chip in the memory system design is shown below. I'll explain you what is chip select, right, in a little while. Again, this is something that we have discussed in our operating systems course in lots of detail. But for those of you who have forgotten it, let me explain what the chip select means. Assume that the memory system has 16 address lines denoted by A0 to A15. What is the range of addresses in hexadecimal of the memory system that can get enabled by the chip select signal? Okay, so first and foremost, what is the chip select signal? So imagine if I have a chip like this. Imagine I have a memory chip. Here it says a RAM chip, right? So here I have a RAM chip. So if you recall, when we saw RAMs along with address bits, look at this, we had some address bits, right? In some cases we had multiplexed address and data pins, right? So there were some pins called as chip select pins also. So what is a chip select pin? If the chip select pin, again, each chip also has, let's say, VCC and ground many times, right? So many chips will have VCC and ground. VCC is the place which you connect to plus 5 volts. So VCC is the pin to which you connect the power supply plus volt. Ground is the place where you connect 0 volts. Plus 5 volts in electronics is nothing but binary 1. 0 volts means binary 0. So chip select is a very interesting signal. So for your RAM chip, so this is your memory chip. So chip select basically means that this chip is selected. So only when chip select equals to 1 can you actually use the addresses. So only when, see, there are many instances. Again, this has been discussed in lots of details in the operating systems course. So this is a question at the intersection of both these concepts, right? So what happens is you could have multiple RAM chips, and since you have multiple RAM chips, you might want to select only one chip at one instance, right? So chip select only when it is equal to 1, that this chip will be selected, and any address that you send here, will be used to figure out what is stored in that address, and that is placed on your system bus, or to be specific, on your data bus, right? So the logic here, it says that, see, look at this, you have 16 bits, right? A0 to A15. Look at this, A15, A14, A13, A12, A11, A10, so on and so forth up to A0, right? Now look at this, what did they do? They have done from A11 to A15, they've connected it to a logical OR. And this blob here basically means negation of this. So if you send 0, it will become 1. If you send 1, it will become 0. That's what this means. So when will this chip be selected? When A15 equals to 1. Look at this. When A15 equals to 1. When A14 equals to 1. When A13 equals to 1. When A13 equals to 1, this blob, as you have learned in digital logic circuits, this is a logical OR gate. So this basically makes this 0 becomes 1. Right? Sorry, this is not a logical OR. This is a logical AND. I'm sorry. This is a logical AND. My bad. So this is a logical AND gate, not an OR gate, right? So now this has to be 0, right? And similarly, A12 also has to be 0. A11 has to be 1. These bits can be anything. Look at this. These bits can be anything here, right? So now let's look at it. We want to represent this in hexadecimal. So these 4 will become 1 hexadecimal. These 4 will become 1 hexadecimal. 4, 4. So the last 4 hexadecimal values can be any F. Can be from 0 to F, right? The last ones can be 0 to F, right? The second 4 bits can be 0 to F. Again, we are only looking at it from the perspective of hexadecimal representation. This is 1 followed by any 3 bits. Your A10, A9, A8 can be any values, right? So 1 is here. That is important, right? 1 followed by 3 zeros. What is 1 followed by 3 zeros? That is 2 power 1 followed by 3 zeros is 8. So from 8 to F is the third hexadecimal digit. What is the first hexadecimal digit? This is 1100. 2 power 0, 2 power 1, 2 power 2 is 4. 2 power 3 is 8. So this is 12. What is 12? 12 is C. Right? So what is the total range of values that I can have here? Let's look at this, right? Again, I have 4 hexadecimal digits, right? Because I have 16 bits here. My first value has to be C. Only when it is C, because A15 has to be 1, A14 has to be 1, A13 should be 0, and A12 should be 0, which means this has to be C. Only when this is C will your chip select be enabled, right? Only then your chip select will be 1. A11 also has to be 1, which means for your second bit you can have values from 8 to F, 8, 9, 10, 11 till F, right? Or 8, 9, A, B, C, D till F. Here you can have 0 to F values, here you can have 0 to F values. Now what is the question here? What is the range of addresses of the memory that can be enabled by the chip select signal? So you have C800, C800, either this or this is the answer, to C8FF. Look at this, to C8FF. So to this, not to C, sorry, from C800 to CFF, not sorry, this is not the answer. So the answer here is C800, let's write this down, right? That's better. From C800 to CFFF. CFFF. This is the address range, right? So C800 to CFFF. Option A is the right option. This is a very good question because this is in the intersection of the concept of memory addressing that you learned in computer organization, the chip select concept that we learned in operating system. Again, chip select concept is also sometimes discussed in computer organization. Again, now you understand what the chip select does, right? Chip select is literally one pin only when it is equal to 1 that this memory chip is enabled, or this memory chip takes the addresses and fills the data bus only when it is selected to 1. Okay, so also digital logic design. This question is in the intersection of all of them because you have a logical AND gate here. Very good question, right? It's an intersection of these 3 subjects. Again, I always like questions which are in the intersection of multiple subjects because that will enable you, because those are interesting questions, because you have to connect the concepts from multiple subjects here. So now let's solve the next question. A processor has 16 integer registers. So it has 16 registers which can store integer values, and 64 floating point registers, right? 64 floating point registers. These registers can store floating point numbers, right? It uses a 2-byte instruction format, right? So 2-byte instruction format, which means the instruction is 16 bits long, right? My instructions are 2-byte instruction format. There are 4 categories of instructions: type 1, type 2, type 3 and type 4. So type 1. Okay. Now before we go there, let's understand, to address these 16 integer registers, how many bits do you need? Because you have 16 of them, you need 4 bits to address these integer registers. Because there are 64 of them, 2 power 6 is 64. So to address these floating point registers, you need 6 bits. Let's write that down here. Okay, because we can use that information. So type 1 category consists of 4 instructions. Type 1 category consists of 4 instructions, each with 3 integer register operands. Okay, 3 integer. So 3 integer operands, right? So each of these operands, how many bits? Integer operands, right? So it requires 4 bits, 4 bits, 4 bits, right? That's what it requires, right? So 12 bits are already taken up by this. Okay, 12 bits are already taken up by these 3 integer registers. Now 4 more bits are left because I have a total of 16 bits and I have 4 instructions here. Okay, let's understand the problem first. Next, type 2 category consists of 8 instructions. There are 8 instructions here, each with 2 floating point register operands. So I have 2 floating point register operands. So 6 bits here and 6 bits. Because to address any floating point register, I need 6 bits, right? That's what I have. So I'm left with 10 more bits here. Okay, so sorry, this is 12. So I'm left with 4 more bits. I'm sorry. So 6 plus 6 is 12. So I'm left with 4 more bits here for the opcode. There are 3 operands here. There are 2 operands here, and this is your opcode. Okay. So let's look at type 3. So type 3 category consists of 14 instructions. It has 14 instructions, each with 1 integer register operand and 1 floating point register operand. So 1 register for integers, 1 register for floating point. So 10 bits here. So I can use the rest of the 6 bits for the opcode. Okay, these are for the operands. Next, my 4th type. Let's write what is type 4. Type 4 category consists of n instructions, each with floating point register operand. So floating point register requires 6 bits, and rest 10 bits are left for my discretion. Now the question here is, what is the maximum value of n? Very good question actually. So here it forces you to think. Now let's see. So how many bits do we have here? Now let's solve this problem step by step. So okay, let me also highlight this, right? So let's go step by step, right? So let's look at number of instructions of type 1, right? Type 1 has 12 bits for addresses, right? It has 12 bits. Look at this. Of the 16 bits, 12 bits are for addresses. So how many possible addresses can you have? 2 power 12 possibilities. Look at this. These address bits, this can be any addresses, right? This could be of register 1, register 4, any register. And these are integer registers, right? That's why they're 4 bits long. So you could have 2 power 12 possibilities here. And it says, for the rest of this, for these 4 bits, there are only 4 type 1 instructions. Consists of 4 instructions only. So the total number of type 1 instructions is 4 into, how many possibilities? Look at this. Of the total 2 power 16 combinations that I can have here. Because 16 bits, right? Of these total of 2 power 16 bit combinations, 4 into 2 power 12 will correspond to type 1. Because there are 4 type 1 instructions. And in type 1 instructions, these 12 bits will correspond to addresses of 3 registers, right? So there are a total of 4 into 2 power 12. So this is 2 power 2. So total of 2 power 14 type 1 instructions are possible. Again, these are here what are we counting? Instructions. See, there are only 4 distinct instructions. But how many bit encodings are possible? Here, this is the number of bit encodings. The total number of bit encodings with 16 bits is 2 power 16. Of these 2 power 16, 2 power 14 possibilities will correspond to type 1 instructions, right? Type 2. Look at this. I have 12 bits here. Look at this. I have 12 bits here. So these 12 bits are addresses, right? These 6 bits and 6 bits are addresses of the floating point registers. This could be any values. So 2 power 12 possibilities. And I have 8 such instructions, right? So into 8. So this is 2 power 15. So of the 2 power 16, 2 power 14 of them will correspond to type 1. 2 power 15 of them will correspond to type 2. 2 power 15 encodings. I'm not saying that 2 power 15 instructions, because what we are counting here also includes the number of addresses, right? Slight difference. We have only 8 instructions, but these 8 instructions have these 12 bits of addresses. These 12 bits could be anything, right? Similarly, let's look at type 3. I have 10 bits for addresses. So 2 power 10 into, I have 14 such instructions, right? So total I have is 2 power 10 into 14. So minus 2 power 10 into 14. Okay. Now this n is what we have to find out. Now if I subtract all of this from 2 power 16 encodings of the 16 bits, 2 power 14 encodings or 2 power 14 bit patterns will correspond to type 1. 2 power 15 will correspond to type 2. 14 into 2 power 10 will correspond to type 3. Now if I subtract all of these from 2 power 16, I will be left with 2048. This is 2 power 11. This is what I'll be left with. Literally this is what I'll be left with. Okay. So which means the number of type 4 encodings are 2048. These are number of encodings. This is not the number of instructions. So in the type 4 instructions, 6 bits are allocated for addresses. Look at this. Because look at this. What does it say? Type 4 instructions consists of n instructions, each with a floating point register. Floating point register takes 6 bits. So these 6 bits, suppose this is n. Let's write the math, right? So how many encodings will correspond to type 4? N into 2 power 6. Right? N into 2 power 6, right? This is what will correspond to. And this is equal to your 2048. This is equal to your 2048. Maximum. N into 2 power 6, maximum value of this is equal to 2048. Because in such an instance, the sum of all these encodings will become equal to 2 power 16. And 2 power 16 is the maximum number of encodings or maximum number of 16-bit strings that I can have. So now what is n? The maximum value of n is 2048 by 2 power 6. So what is this? This is 2 power 11 by 2 power 6, which is 2 power 5. 2 power 5 is 32. So the answer here is 32. This is a slightly twisted question. You have to read the question very, very carefully. Otherwise, it's very, very prone to making mistakes. Here the key idea here is we looked at the number of bit patterns that are possible. We subtracted how many addresses of type 1 we can subtract, what are the number of bit strings or bit patterns that correspond to type 1 instructions, type 2, type 3 and type 4. Now the sum of all these 4 should be equal to 2 power 16, and that's what we solved it to be. So the answer here is 32. Very, very good question. Slightly tricky question, but a very good question. So let's look at this question. A processor can support a maximum memory of 4 GB, right? 4 GB is the maximum memory, where the memory is word addressable. Cool. And the word consists of 2 bytes. Look at this. The word in your memory consists of 2 bytes, right? And the total memory that it can address is 4 GB. The size of the address bus of the processor is at least dash bits. Okay, if it is 2 bytes, how many rows are there in this memory? If you think of your memory as a table, what is this? This is 2 power 2 into 2 power 20, right? So this is 2 power 30, right? This is gigabytes. So GB is 2 power 30. So 2 power 2 into 2 power 30 bytes. So what is this total thing? 2 power 32 bytes. 2 power 32 divided by 2. Because this whole size is 4 GB. This whole size is 4 GB. So this is, each row here is 2 bytes. Each row or each word here or each cell here is 2 bytes. Which means how many rows you have here now? 2 power 32 by 2, which means 2 power 31 cells you have. 2 power 31 cells or words or locations is what you have. And to address 2 power 31 cells, you need your address bus to be 31 bits. At least 31 bits. If you have more, obviously you can always address everything. So you need at least 31 bits to address this whole memory. Very simple question. You just have to understand what is the total capacity of the memory, what is the size of each word, how many cells are there, and to address these many cells, how many bits do we need? Very simple, straightforward question here. Okay. Now let's look at the next question. It says a processor has 40 distinct instructions and 24 general purpose registers. Cool. A 32-bit instruction word. So you have 32-bit instructions, right? So you have 32-bit instructions here, right? You have 32-bit instructions here. It has an opcode, right? It has an opcode. So it has an opcode and 2 register operands. So I have register 1, the second register, and an immediate operand, right? I have a 4th operand also. So let's call it the immediate operand. This is like the this is like the, we have seen something like this, right? We've seen something like this when we studied 4 address format. We have seen something like this when we saw 4 address format, where we had an opcode, 3 addresses and another operand here, right? So now the question here is the number of bits available for the immediate operand is. Let's solve this. So opcode, what does it say? 40 distinct instructions. So for 40 instructions, how many bits do I need? Look at this. 2 power 5 is 32. 2 power 6 is 64. So if I have only 5 bits, I can only represent 32 bits. If I have 5 bits, if I have 5 bits, I can only represent 32 instructions. But I want to represent 40 instructions. Because I want to represent 40 instructions, I need 6 bits mandatorily. Of course, all these 64 combinations will not be used. Only 40 of them will be used. And I have 24 general purpose registers, right? So what is 2 power 4? 2 power 4 is 16. 2 power 5 is 32. So to address these 24 registers, I can't address it with 4 bits because with 4 bits, I can only address 16 registers. I need 5 bits here. So this will be 5 bits. This will also be 5 bits. So what is the size that is left for this now? 6 plus 5 plus 10, 16. 32 minus 16, right? This whole, look at this, it says that the instruction length is 32-bit instruction word, right? So 32 minus 6 plus 5 plus 5. So this is 16, 32 minus 16 is 16. So the answer here is 16. That's the size. The question is the number of bits available for the immediate operand field is 16 bits. Very simple question here. So now let's look at this question. It says, consider a processor with 64 registers and an instruction set of size 12. So which means I have 12 instructions and I have 64 registers. To address 64 registers, you require 6 bits, right? Each instruction have 5 distinct fields, okay? One opcode, so I have opcode, right? I have 2 source register identifiers. So source register 1, source register 2, one destination register, and 12-bit immediate value. So I have 12-bit immediate value, right? So I have 12-bit immediate value. Each instruction must be stored in memory in a byte aligned fashion. Okay, cool. If the program has 100 instructions, the amount of memory in bytes consumed by the program text is cool. So look at this. I have an opcode and it says I have 12 instructions, right? To store 12 instructions, what is the minimum number of bits I need? 2 power 3 is 8, 2 power 4 is 16. So I at least need 4 bits here. Look at this, I at least need 4 bits. If I have only 3 bits, I can only have 8 instructions. But I have an instruction set. What is an instruction set? Set of all instructions. And the set of all instructions is of size 12, which means I have 12 instructions, which means I need 4 bits here. The register 1, 64 registers are there, so 6 bits will be taken up by this, 6 bits will be taken up by this, 6 bits will be taken up by this, and we are told that the immediate is already 12 bits. So what is the size of each instruction now? 4 plus 18, so this 18 plus 12, right? 18 plus 12 is 30, right? 34, right? 34 bits is the size of each instruction, right? So 34 bits is roughly, if I divide it by 8, I get bytes. So this is 8 4s are 32, 2 by, so 4.25 bytes is what I have, right? Per instruction. This is per instruction. Now I have 100 instructions, which means I can store this in 425 bytes. Very simple question, right? So we have 425 bytes here, right? But here there again, so you might be tempted to write the answer as 425 bytes, but there is a small twist here, which is, so it says each instruction must be stored in memory in a byte aligned fashion. Look at this. What does this byte aligned fashion basically mean? Which means I can't see if I have 4.25 bytes, 1 byte, 2 bytes, 3 bytes. The 4th byte, I can't stop it here and I can't say that my next instruction starts from here. I can't say that, right? Okay, so 4.25, right? So this is first byte, second byte, third byte, fourth byte. In the 5th byte, I can't accommodate 0.25 bytes. Look at this, I can't accommodate 0.25 bytes for one instruction and 0.75 bytes to the second instruction. That's not allowed, right? You can't do that. How does the CPU now fetch everything and decode all of this? So when it says byte aligned fashion, it means that each word in my memory is 1 byte long. So even though it requires 4.25 bytes per instruction, in memory it will be stored across 5 bytes. In memory. See, I require 34 bits, right? So even though it requires 4.25 bytes, very common mistake that people make is people answer 425 bytes here, which is not correct. Because you can't allocate part of a byte for one instruction and another part to other instruction. You can't do that. Right? So these instructions are all 5 byte instruction. Just that these 0.75 bytes here are useless. They're not used for anything. They're just left blank or some random value will be present here. So if each instruction requires 5 bytes, 100 instructions will require 500 bytes. So the correct answer here is 500 bytes and not 425 bytes. Initially I showed you the wrong answer because it's a very, very common mistake that many of us will commit. Okay. Now let's look at the next question now. So what does this say? For computers that are based on 3-address instruction formats, okay, we know what is a 3-address instruction, right? You have opcode, you have one address of the operand, first operand, address of the second operand. This is your 3-address format. Each address field can be used to specify which of the following. You can specify a memory. This address can be memory location. Cool. Why not? A processor register. Yes, it can be. An implied accumulator register. No. See, we never use accumulators here or here. As part of my addresses either refer to registers or to your memory locations. They don't explicitly tell about the accumulator itself. They don't do that. Right? They don't do that. So S3 is not the right option. Only S1 and S2. These addresses can correspond to the memory address or the register. So A is the right answer here. Either S1 or S2. Right? So S1 or S2, both of them are correct. Right? But not S3. That's very, very important. Okay. Now let's look at the next question here. So this question says, I have two processors P1 and P2. Okay, so I have two processors P1 and P2 executing the same instruction set. Assume that under identical conditions, for the same input, a program running P2 takes 25% less time. Oh, so same program takes 25% less time on P2. Cool. Okay, so let's keep that in mind. But incurs 20% more cycles per instruction. Okay, so let's keep that also in mind. Okay, as compared to the program running on P1. If the clock frequency of P1 is 1 gigahertz, then the clock frequency of P2 is. Oh, this is like a very aptitude-like question. Even though it is based on your computer organization, it's a very aptitude-like question. So let's see this. So let's talk about P1. P1 is a 1 gigahertz processor. Okay, which means what is the time period? What is the clock cycle period? Look at this. What is this period now? Look at this. It is doing 1 giga cycles per second, right? So it's doing 1 giga cycles per second. This is its frequency. So what is this time interval or time for one clock cycle? What is this? This time interval here is 1 by 1 gigahertz. 1 by, what is 1 giga? 10 power 9, right? 1 by 10 power 9. So this is 1 nanosecond. So the time interval here is 1 nanosecond. Okay. So what is asked of us? We are asked what is this frequency? This is what is asked. So you can compute this frequency if you know this time interval for process 2. If you know this, you can compute this, right? Because frequency is nothing but 1 by t. Very simple. Very simple logic here. That's it. Again. So now it says, okay, there is a twist here. What does it say? A program running P2 takes 25% less time but incurs 20% more clocks per instruction. Okay, so let's go through this. Suppose, so for P1, let's assume I'm running one instruction per clock cycle. So it says incurs 20% more clock cycles per instruction. Okay, so let's assume this requires 1 clock cycle per instruction. Okay, this will require 1.2 clock cycles per instruction, but incurs 20% more clock cycles per instruction. Okay, that's what it says, right? If this requires 1 clock cycle, in 1 clock cycle it will finish an instruction. But this again, this has a different clock cycle. Remember, suppose this has a different clock cycle of its own. This takes not 1 clock cycle per instruction, but 1.2. Because this is 1 clock cycle, right? This is 1 clock cycle now. Instead of 1 clock cycle, it requires 1.2 clock cycles per instruction. Okay. But even though it takes more clock cycles, this is executing faster. It says takes 25% less time. So if this takes 1 nanosecond, this only takes 0.5 nanoseconds to complete. Right? Look at this. Because it's taking 25% less time. So even though it requires more clock cycles or more clocks per instruction, it is completing fast, which means its frequency must be significantly higher than this, first and foremost. Okay, simple logic. So D cannot be an answer, but you have 3 options. Now how do you figure this out? You have to be careful here. Again, this is more like an aptitude question, as I told you, right? So let's assume there is an instruction which takes 1 nanosecond here to complete. Okay, the same instruction is completing faster here. So the same instruction is taking 0.75 nanoseconds to complete here. But the same instruction will require 1.2 clock cycles here. So 1.2 into, suppose let's assume the time interval here. Let's call this T2. Let's call this as T2. Okay. So look at this. My point, see, I'm finishing. Suppose there's only one instruction. Suppose let's assume the program has only one instruction, just for simplicity. Okay, that one instruction, let's assume this completes it in 1 nanoseconds because it requires 1 cycle per instruction. The same program, this will complete in 0.75 nanoseconds. So this 0.775 nanoseconds equals to 1.2 into whatever is the time interval for this, 1.2 into T2. Because this is your T2, right? This is your T2. This whole width is your 1.2 T2. Because it requires, look at this, to finish one instruction, it requires 1.2 cycles. And this is the time for each cycle. And this whole thing is just 0.75 nanoseconds. So if you solve for this, what do you get? You get T2 equals to 0.75 nanoseconds by 1.2. This is what you get. Now what is the question? I want F2. I want the frequency of this. How do I get the frequency of this? Just invert this. Frequency is 1 by T. Right? What is this frequency now? 1.2 by 0.75 nanoseconds. 1 by nanoseconds is what? 10 power 9. Right? Because nano is 10 power minus 9, right? So these many hertz. So 10 power 9 hertz is gigahertz. 1.2 by 0.75. What is this? 0.75 into 0.75 into 1.6. Okay, so this will come to 1.6. So this will become 1.6 gigahertz. The answer here is A. It's a very simple aptitude question. This is a very aptitude-like question in the context of computer organization. Very nice problem. Okay, very fun problem to solve. Slightly tricky. It's very, very easy to make a mistake here. If you don't write all the details here, and if you have not understood the question, like, because a lot of details are just given in one sentence here. It's very, very easy to make mistakes here. Okay, so let's look at the next question now. So what does the next question say? A machine has 32-bit architecture with one word long instructions. Okay, one word long instructions. So because it's a 32-bit architecture, I'm assuming that this is also 32-bit, right? Because one word, 32-bit and one word, right? It has 64 registers. Okay, let me highlight them. 64 registers, which means 6 bits for each register, each of which are 32 bits long. Each of them are 32-bit long. Of course, because the word size is 32-bit, each of them will be 32-bit long. It needs to support 45 instructions. Okay, so to support 45 instructions, how many bits do I need? I need 6 bits. Because 2 power 5 is 32, 2 power 6 is 64. 45 lies in between both of them. So I need 6 bits to support 45 instructions, which have an immediate operand in addition to 2 register operands. So I have an opcode. Look at this. I have an opcode. I have 2 registers, R1, R2, and I have an immediate also. Okay, assuming that the immediate operand is an unsigned integer. Okay, this has to be read as an unsigned integer. The maximum value of the immediate operand is. Okay, let's write this down. So this opcode, 45 instructions, so 6 bits are taken up by this. I have 64 registers, so 6 bits for this and 6 bits for this. Now, so 6 3s are 18, 18 are consumed. So how many are left now? 32 minus 18. So only 14 bits are left for my immediate address, right? For my immediate operand, right? So the last operand is called the immediate operand. 14 bits are left, right? Now, in these 14 bits, I need to consider this as an unsigned integer. So what are the values that I can store in 14 bits? 0 to 2 power 14 minus 1. That's the range of values I can store in 14 bits. The maximum value of the immediate operand is, okay, the maximum value is 2 power 14 minus 1. What is 2 power 14? 2 power 14 is 16384. You can verify this. So 2 power 14 minus 1 is 16383. Right? So the answer here is 16383. Simple question here.